Dropping a lump of putty on a frame. A 0.15 kilogram frame, when suspended from a coil spring, stretches the spring 0.04 meters. Okay, so this spring is stretched 0.04 meters. A 0.2 kilogram lump of putty is dropped from rest onto the frame from a height of 30 centimeters. Find the maximum distance the frame moves downward from its initial equilibrium position. Okay, so if I draw the free body diagram of the frame before dropping the lump of putty, there are two forces I would identify. That is the weight of the frame pointing down, and then there is the restoring force on the spring, which is pointing up in reaction. So if I call this vertical axis as my y-axis, then I can see that there will be mg mass of the frame times gravitational acceleration pointing down, and there will be the spring force pointing up. And the net force on the y-axis is 0 because we have an equilibrium situation here. This is equilibrium. So the spring restoring force K times delta y magnitude will be equal to mg. So it will be balancing the weight of the frame. We can see that K, the spring constant, will be the ratio of the weight to the stretch in this equilibrium position. So the weight of the frame is 0.15 kilograms times 9.8 meters per second square divided by the equilibrium stretch 0.04 meters. So let's call this the stretch in the equilibrium position, and that gives us 36.75 newtons per meter for the spring constant of this coil spring. Now let's concentrate on the collision between the frame and the putty. So frame plus the lump of putty. So in this system, during the time of the collision, because I have an equilibrium situation here, as this is hitting the frame, the external force on the system is 0. At the time of the collision. Why? Because we have the net external, the net force on the y-axis is 0. The spring force is balancing the weight of the frame, and therefore the conclusion is that in this collision process, a linear momentum must be conserved. Okay, so about this putty being dropped, it's released from rest onto the frame 30 centimeters below it. We have the gravitational acceleration g pointing down, and this is going to be a free fall onto the frame. So we can write the distance we travel is 1/2 gt square, that is 0.3 meters. Therefore, the time of flight would be 0.6 divided by g square root. And the final speed of the putty as it hits the frame will be gravitational acceleration times the time of flight. So it's g 0.6 over g square root. That will be square root of 0.6 g. That gives us square root of 5.88 meters per second. And if we write the conservation of linear momentum, the linear momentum of the putty right before the collision will be mass of the putty multiplied by its velocity of the putty. The magnitude is squared 588. It's in minus j hat direction as it's dropping onto the frame. So what was the mass of the putty? It's 0.2 kilograms. So 0.2 square root 0.6 g in minus j hat direction is the momentum of the linear momentum of the putty. The final momentum of the system will be mass of the putty plus mass of the frame multiplied with the final velocity. Okay, so let me call this mass of the frame mf here just to be consistent, and mass of the putty, let's call it mp. So this becomes mp plus mf times the final velocity of the system. So the final velocity after the collision, right after the collision, will be 0.2 square root 0.6 g in minus j hat direction, initial linear momentum, divided by the total mass 0.2 plus 0.15, 0.35 kilograms. Okay, so after this, so this is just after the collision. Okay, so this is the linear momentum of the putty just before the collision, which is equal to the linear momentum of the system just after the collision. So there is no friction in this process, so we can say that since there is no friction, it's an elastic coil, we must have energy conservation. So energy must be conserved. All right. So if I write the change in the mechanical energy of the system should be 0, that means 1 over 2 total mass m total v final square, the kinetic energy of the system, plus the potential energy stored in the coil, 1 over 2 k delta y equilibrium squared, because we had an equilibrium stretch of 0.04 meters on the spring, plus we have potential energy m total g delta y2, as the system will putty plus the frame will come down a distance delta y2, which is what we're after. Maximum distance the frame moves downward from its initial equilibrium position, so that's the distance the system will come down. This gives us a potential energy contribution. And finally, if it is the maximum distance we are after, maximum distance delta y2 the system will travel, that means the final kinetic energy will be 0. Therefore, we will have just the potential energy stored in the spring, which is 1 over 2 k delta y equilibrium plus delta y2 square. Okay, so this is equal to 1 over 2 m total v final square plus 1 over 2 k delta y equilibrium square plus m total g delta y2, the potential energy, is equal to, so if I open this up, this is going to be 1 over 2 k delta y equilibrium squared plus k delta y equilibrium delta y2 plus 1 over 2 k delta y2 squared. Now you can see that these terms will disappear and I will be left with this equation 1 over 2 k delta y2 squared, so that's this term, and then I will take this term to the right hand side, so that becomes plus k delta y equilibrium minus m total g delta y2. So I've collected all the delta y2 terms, and this goes to the right hand side as minus 1 over 2 m total v final square is equal to 0. So we're going to solve for delta y2 from this equation. Okay, so whenever I see a 1 over 2k, that is 36.75, the spring constant divided by 2, so that will be replaced with 18.375. The term k delta y equilibrium minus m total g is 36.75 times equilibrium stretch 0.04 meters minus total mass 0.35 kilograms times 9.8, and this term is minus 1.96, and where I see 1 over 2 m total v final square, this is 1 over 2 times 0.35 times v final square. So what was v final? V final is here, so we take it square. It will be 0.04 times 0.6 times 9.8 divided by 0.35 square. So it was this term. If you take it square, you obtain 0.04. So this square root disappears, 0.6g divided by 0.35 square. And that gives us 0.336. So we can plug in these findings. So we have 1/2 k delta y2 square, that is 18.375 delta y2 square, and then this term multiplied with delta y2 is minus 1.96 delta y2, and then the last term is minus 1/2 m total v final square kinetic energy term, which is minus 0.336. This equals to 0. And we can solve this quadratic equation. Delta y2 is equal to minus b 1.96 plus or minus squared b squared minus 4ac divided by 2a. So this will be divided by 2 times 18.375. So we're going to take the positive root only. The negative stretch is unphysical. So we can obtain b square 1.96 square minus 4ac plus 4 18.375 times 0.336 square root b square minus 4ac divided by 2a, 2 times 18.375, and the final answer we obtain is 0.199 meters, so it's approximately 0.2 meters of additional stretch from the equilibrium position. Okay, so in this problem, first we have an equilibrium condition satisfied by this frame and this elastic coil. If we look at the free body diagram, we see that the spring force is balancing the weight of the frame. The net force on the y-axis is 0, and this allows us to calculate the spring constant. When this putty comes down, it's going to accelerate under the influence of gravitational force, and when it hits the spring, there is no external force acting on the system. Of course, there will be a collision force developing between these two, but because there is no external force acting on the system, we can say that this is going to lead to conservation of linear momentum. Okay, so at this time, when this putty hits this frame, it exerts a force on the frame exerts a reaction force, and apart from this internal force between the putty and the frame, there is no external, there's no net external force. And the free fall of the putty basically results in 1/2 gt square as the change in height of the putty, and the final speed of the putty will be g times t, because we started from rest, it's dropped from rest, and that means the linear momentum of the putty was mass of the putty times its velocity right before the collision. This must be equal to the total mass. M total is mass of the putty plus mass of the frame times their common velocity v final. So this v final is the velocity just after the collision. And from that point on, the system, the frame plus the putty, will have a kinetic energy, and therefore they will start coming down, and this energy will be transformed into potential energy of the spring by causing an additional stretch. It already had a 0.04 meter stretch. There is an additional stretch, and for the maximum stretch, we will have the final kinetic energy of the system 0. So at the maximum stretch point, we have all of the kinetic energy converted into potential energy. So there is no friction on this system, so energy must be conserved. The total kinetic energy of the putty and the frame right after the collision, plus the potential energy stored in the spring, 1/2 k delta y equilibrium square, plus the potential energy with respect to the minimum point of the travel, and total g delta y2 must be equal to the final potential energy stored in the spring, 1/2 k delta y equilibrium plus delta y2 square. So basically we can plug in the numbers and solve this quadratic equation for delta y2 to obtain our additional stretch with respect to the equilibrium position.